Okay, but like I said, in this class so far, we've studied the different changes that you can get in a graph or a table for linear, quadratic, and exponential functions. So this kind of, again, puts it all together into one place so that we can start comparing the function models together. Because not always am I going to tell you what kind of function it is. Your job is going to be to decide what kind of function best represents your data. For the most part, it's really pretty simple because we know what the three shapes should look like. If you are dealing with a linear equation, obviously the points will be essentially linear. So they would go in a line-ish. Line of best fit would be as close as possible. In a table, we found out that if you found the difference between all of these things, it would be relatively constant. Now, if you actually did that for this table on your notes, you'll notice it's not an actual constant rate of change because this is not a pretty function, it's data, but it's relatively constant. So my rate of change is relatively constant. That means it has a slope. Okay, so that's linear. Got a straight line, essentially linear. We have a constant rate of change. For quadratic, we know that that looks like a parabola. It's a U-shaped pattern or a flipped over U-shaped pattern. So the picture of it makes a lot of sense for us. When we did this on a table, we found out that the second differences are the same. But the way that we talk about the second differences is we say that the rates of change are changing at a constant rate. So we're not just straight up talking about the rate of change, we're talking about the change of the rate of change. That's when we knew we were dealing with a quadratic set of data. The third and most recent type of function we learned about was exponential. Exponentials make curves, one-sided curves that are entirely increasing or entirely decreasing the whole time, either concave up or concave down, no changes. Their tables were created by multiplying, essentially by the same number every time. For a perfect exponential, yes, you would have to multiply by the same number every time, but for data, you're going to look for things that are roughly proportional. That's the word we had been using when we described why something was exponential, because the change is proportional. This is because of the repeated multiplication that creates one data to the next, one output to the next. Now, what's really important here is that you recognize the shapes, because a lot of times what you're going to be doing with data is looking at the scatter plot created from your different data points, and then you need to decide if it's linear, quadratic, or exponential. Obviously, the shape will tell you everything. If you're given a table, you look for the differences like we've been doing, and then we can say the different words that we have. Rate of change is constant, the change in the rate of change is constant, or the rate of change is proportional. Sound good? So let's see how that looks. Now again, today, it's not going to be super duper perfect. We're going to be estimating. We're going to be finding essentially the line of best fit, but sometimes we're going to call it the curve of best fit because it's not always going to be a straight up line. We're looking for what is most appropriate for the data. So if we plot these coordinate points, classic x's and y's, we'd have 0, 11, that's up here. We'd have 2, 8.2, just do your best, 4, 5, 6, 2.3, and then 8, -1. I know I'm human, so those aren't the most perfect plottings that we could have if we used our calculator or another graphing software. It would be absolutely perfect, but we're human. However, we can look at this data. Does this data look essentially linear, quadratic, or exponential? Linear. Yeah, don't overthink it. This would be best represented by a linear graph. That would be what is most appropriate for this data. We could technically run a regression in all three forms, but the most appropriate regression is going to be linear since the dots literally go in essentially a straight line. That make sense? Let's do the second one. So part B, again, if we just classic plot those points, -1, 2, 1.5, 5.5, do your best, 4, 10.5, I think I missed, no, that's right. 6.5, 5.75 here-ish, and then 9, 2.25. Out of the three options I gave you today, is this data best represented by linear, quadratic, or exponential? Quadratic. Yeah, why quadratic? Because it like curves. It goes up, it comes down. If it has a turning point, it's going to be quadratic because exponentials don't have a turning point. So we know that this is best represented. It is most appropriate to use a quadratic to describe this data. Y'all got the bottom two? Again, just classic plotting points, making sure we know what is best represented or most appropriate for the data. I'll give you some time. All right, so for these, what do y'all think? I've got mine plotted. What did you say for both of them? Exponential, nice, yeah. So both of these graphs were best represented by an exponential function. So we know if we were moving on from this problem and saw the scatter plot and then we needed to create a regression, we'd be like, we should choose the exponential button on my calculator, not the linear and not the quadratic. So we're starting to have to make that choice for ourselves based on what the data looks like. Okay, we'll do this in our calculator eventually. But just looking at the data points, we're going to be able to choose the most appropriate model. Another thing we can use to help choose an appropriate model is something called residuals. Now, if you think back, probably like a month ago at this point, I gave you a purple piece of paper with a bunch of calculator skills on it, and I said the front would teach you how to do a regression, and the back we would get to later. It's something called residuals. That's back. Okay. So you have the steps on that purple calculator sheet on how to create your own residuals, which is not what we're doing today. We're actually just interpreting residuals. We'll get to creating them again probably the next time we see this concept. But a residual, let's highlight that word, reminds us that we are using these models to predict the future. Not actually see the future, but predict the future. So we could over or underestimate the future based on what we get from our equation. Now, this difference between the predicted value and the actual output value is called the residual. You will 1000% need this formula on the test you're taking next time. A residual is found by taking the actual output value, something from a table, something from a word problem, and subtracting the predicted output value that your equation gave you. So like last time when we had to predict the future, and you like typed y1 parentheses something into your calculator and it gave you a number, that's your predicted value. We want to see how off our answer is. What the residual is comparing an actual answer from real life to our predicted answer from our model. That's called a residual. Now you'll see here it is in words because I felt like that was a little bit easier to understand, but in symbols, in textbooks, if you go online and look it up, it's going to say something probably like this, where it says the actual output value y. Y is always the output value. Minus y hat. You put a little hat on it because it is the predicted value. So if you see y hat somewhere on the internet when you're searching around, that's what it's talking about, the predicted output value. Sound good? Let me show you how to use it or the kind of questions you might see. You're given this table on the next page and it says the weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values of the weight, WT, in kilograms of a particular newborn baby are given in the table on the right, where T represents the number of months since birth. Part A, use a regression capabilities on your calculator to find a linear model. Oh, look, it even told us what kind of model this time. We didn't have to figure it out. A linear model of the form y equal to a plus bx for the weight in kilograms of this particular baby x months after birth. I want to bring to your attention that this is not regular y equals mx plus b. So on your calculator, when you run the regression, you're going to make sure you choose that version of a linear regression. I'm going to give you some time to remember how to do that. You have it in notes somewhere and you got neighbors near you. Go ahead and just do part A and write the regression for the growth of this baby, the weight of this baby. So remember, we're choosing option 8 on the stat calculate screen because that's the linear regression in the form it asks me for. Option 4 is also a linear regression. That's the one you probably used in Algebra 1, but we're going to continue to use this one because that's exactly what it says in the problem. We should have gotten that the weight of the baby can be represented by y equal to 3.34 plus 0.8x. Is that what you guys got? Okay, fabulous. So we have our linear equation that predicts the weight of this baby. Part B says to use the model found in Part A to predict the weight of this baby 2.5 months after birth. Okay, there's a shortcut for doing this because obviously if I'm giving you months, that just means I want you to plug this in for T or for X, depending on what letter you used. But in a calculator, what's the shortcut to be able to do that faster? What can you type in your home screen after you've run a regression to plug a number in pretty quick? Y1 parentheses and then the number. Okay, if you did the regression correctly and you saved it in Y1 like I've been asking you to on that store regression equation, you should be able to press alpha trace enter, parentheses, 2.5, press enter and give me an answer. Yeah, is it 34? Yeah, 5.34 kilograms. All right, so we're assuming, based on our model, that a baby 2.5 months after birth is going to weigh 5.34 kilograms. Part C is going to ask you to decide if that was an overestimate or an underestimate of the actual weight of the baby. Here's how I know this. It says the actual weight of the baby 2.5 months after birth was 5.5 kilograms. What is the residual? There's our new word. Where is the residual for this weight? Did our model underestimate or overestimate the weight of this baby? Okay, our residual formula says that we can find a residual if we take the actual value and we subtract the predicted value. What is the actual value of the baby, or weight of the baby? 5.5 kilograms. And what was our predicted weight? We predicted it would be 5.34. So when we plugged in 2.5 to our equation, we got 5.34. But they actually weighed a baby, and it was 5.5. So 5.5 minus 5.34 is 0.16. So my residual is this number here. That's the residual. Now we interpret the residual. Did we overestimate or underestimate the weight of the baby? Yeah, we underestimated. Yeah, we thought it would be 5.34 when actually it was 5.5. So our number was lower, which means that this is an underestimate of the actual weight. Underestimate. Parts D and E are kind of like copy-paste of B and C because I want to make sure we actually understand this. So this one's all you. I want you to do D and E. Answer all the way through parts D and E. All right, let's chat. When we did this again, so we already had the regression in our calculator. So really, we should have just done Y1 of 3.5 again because we still had it saved in our calculator. Is that what y'all did? What'd you get when you did Y1 of 3.5? 6.14 kilograms. All right, so that's what we predict the weight of the baby will be, but now we need to decide how good that prediction is. So we look at the residual. The residual for this is always going to be the actual value minus the predicted value. Now in this question, it says the actual weight of the baby is 6.09 kilograms. So when I go to plug that in here, I'm using a different actual weight because I'm checking a different month. So this would be 6.09 minus the 6.14. So again, that's my actual weight minus the predicted. And we should get that the residual is negative 0.5. Is that what y'all got? Fabulous. Now, did we overestimate or underestimate? We overestimated. That's why our residual was negative. So a residual, again, is just checking how good our data is. Let's draw some conclusions about residuals, because yes, ma'am?
Does it always have to be negative if it's overestimated?
I am so glad you asked that, because yes. If we put this into a conclusion right here, did y'all hear her question? Is it always going to be overestimated if the residual is negative? Yes. So if we think about the actual formula we're using for a residual, if our actual value is, if our predicted value is more than our actual value and we're subtracting it, we're always going to end up with a negative number. So if we were to plot our residuals, which is something we will do, again, not really today, we're going to be reading plots of residuals today, we need to know what kind of information it's telling us. Everything down underneath the x-axis is an overestimate of the actual value because those are negative numbers. Anything above 0 or above the x-axis is going to be an underestimate. And that's again because you're subtracting your prediction from the actual value. So if you end up with a positive number, your actual value was more, so we underestimated it. Now what's really, really, really important here, not only just the over and underestimate part of a graph, is understanding what a residual tells you. I said at the beginning of this lesson, part of our job today is to decide what the appropriate model for our data is. A residual will also help you do that. Put a whole bunch of stars, circle, star, underline, all the things along this bolded sentence right here. This is the most important thing out of this. If a model for a given set of data is appropriate, the residual plot will appear without pattern. It should be straight up random. If all of those dots are in a line, it's wrong. If they're in a curve, it's wrong. If they make a quadratic, it's wrong. A residual should be random. If your residual is random, just kind of like a glob of dots, you've probably picked the correct model for that data. If you can see a clear pattern, then the model you chose was not appropriate for that data. So looking at residual plots is going to be very helpful for us to be able to decide if things are appropriate or not. One more thing, just so that it's all in one spot for later when you go back through your notes, I want you to write one more thing down here. Since we're looking at coordinate points on a residual plot, every coordinate point stands for the input value of the actual function, comma, the residual from that output. So when we're plotting points on a residual or we're reading points on a residual graph, we're talking about the x value being the input value, the y value being the amount of residual you have from that output value, which is kind of funky. Okay? So the next page is going to show you the kinds of questions I might ask you about residuals. The first one gives you a residual plot. Okay, so this is what a fully graphed residual plot might look like. It says, an exponential regression was used to model a data set. The residual plot for the exponential regression model is shown above. Which of the following is, well, write the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot. So we're going to fill in the blanks here. What do you notice about the dots in this residual plot? Do they make a nice pretty straight line? No. Do they make a curve? Do they make a quadratic? No, these are seemingly random and without pattern. So the way that we would answer this, or the conclusion we would draw, is that this exponential model is appropriate for the data because the residuals show no pattern. So words you're going to have to start using is most appropriate or not appropriate, does show a pattern or does not show a pattern. We want it to be appropriate when there's no pattern showing.
Isn't that bad?
That there's no pattern? In the residuals, that's a good thing. Remember, this is not the actual data.
Doesn't that mean it's really inaccurate?
So again, this is speaking about the residuals. Like we're never gonna, if it was, okay, I see what you're asking. If this was a linear equation like y equal to x, your residuals would all be 0 because it's perfect. But we're talking about data, and data will never follow a particular graph. We're just gonna have a regression that best predicts the graph. So there will always be a little bit of inaccuracies when we're actually using real life data. Does that make sense? So doing residuals for like not data stuff doesn't really help us because residuals tell us the inaccuracies in our graph, which will come from data input, not necessarily like input outputs like we've done since forever. Yes?
So what if the residual is 0?
That means that you have like a perfect graph. We won't be asked a question about residuals for that kind of thing because we wouldn't have used data for it. You would get like a straight up input output list from an equation. That's a good question. Okay, let's look at the next question here. Example 4 gives you 3 residual plots. It says a group of AP Pre-Cal students, oh look, that's you, used a set of data to create linear, quadratic, and exponential regression models. After creating the 3 models for a particular set of data, the students created these residual plots for each model type above. Based on the 3 residual plots above, which model was most appropriate for the data? Give me a reason. Okay, so we are creating from the same data. So I hand you one table and I say pick which one is the best. And you decided to do all linear, quadratic, and exponential at the same time because you weren't sure. So you plotted their residuals, and the residuals look like this. What do you notice about the linear regression's residuals? What do you notice about all these points? Do they have like a pattern? It's kind of quadratic and kind of weird, but there's a pattern to it. What do you notice about the quadratic ones?
It goes up or it goes down.
Yeah, it's got a polynomial pattern here. Kind of weird. What do you notice about exponential? It's like everywhere. So which was the best model for us to use for our data? The exponential. We want the one with no pattern. A residual that shows you no pattern is good, which is weird because you want a pattern in your actual data, but you want no pattern in your residuals. So the way we would answer this is we would say, in a sentence form, the exponential model is most appropriate for this data because the residuals show no pattern. And just to emphasize it because it's our notes, remember we want residuals to have no pattern. That's the key. Now this last question is going to ask us to think about a coordinate point on a residual plot. It says, students in a pre-cal class measured each other's heights and arm span in centimeters. The students calculated a linear regression with the heights and the input values and arm spans as the output values. So height is the input, arm span is the output. Given the residual plot has a point labeled P at the coordinates 175, 23.4, what does point P indicate in the context? Here's what I want us to remember. On a residual plot, a coordinate point is going to always tell us the input, comma, the residual. So we are talking about an input value of 175. This particular function has input values as the heights. How do I know that? It says it right here. The height is the input value. That means that we have a residual of 23.4 when we have the output value at the input value of 175. Here's our conclusion. Because point P is above the x-axis, for a student with a height of 175, that's the input, the model blanks the actual arm span by a value of 2.34. I'm looking for the word overestimate or underestimate. Since this is a positive number as an output, it's going to be above the x-axis. When we had those residuals, what was happening above the x-axis? Was that the overestimate or the underestimate? This was the underestimate, and this one was the overestimate. So we know that because we have a positive number as my output for a residual, that this underestimates the actual arm span value by 23.4 centimeters. So remember, we're not looking at input outputs, we're looking at inputs residuals. The difference between the predicted value and the actual value. Okay, so next class we're going to have a test over what we've covered so far in Unit 2. Obviously, we need a little bit of practice with residuals. So if you look at the test review I gave you, it starts with a bunch of questions about residuals. I want you to do those questions first because I'm assuming we have questions about them. Once you get through the questions about residuals, you could go back to the homework assignment that maybe you haven't finished, then you need some more help on. We're going to ask individual questions from the homework, not as a class. But I want you to work for the rest of class, making sure you're prepared for this test next time. Start with the residual questions on the test review. Yes? You can work with the people around you. You can ask me questions, but today, from here on out, is going to be a study day to prepare ourselves for that test.